Lighthouse Scientific Education presents a lecture in the Energy series. The topic, Kinetics. Material in this lecture relies on an understanding of the previous lectures, energy and reactions, thermochemistry, thermodynamics and advanced concepts, acids and bases, advanced concepts. The topic of the lecture centers on the speed of a chemical reaction. As such, a review of the fundamentals of the chemical reaction is offered. That is expanded into an introduction to kinetics with a discussion on reaction rates. This is tied into the energy of a reaction from the perspective of collisions. There are several factors that affect reaction rates. The change in rates will also be viewed from the perspective of changes in concentrations. The lecture ties off with a connection to the next lecture, equilibrium. At this point in their study of chemistry, the student should be familiar with the chemical equation. Here is the formation of water from elemental hydrogen and oxygen. A review has the reactants of the equation as the species present before the reaction, and the products as the species present after the reaction. We've also seen that many reactions are reversible. Under the right circumstances, the products can react to reform reactants. It is acceptable to write this reaction with the water as the reactant, but a better way to handle a reaction that goes in both directions is to write one reaction with two arrows, or one double-headed arrow. The reaction of reactants to products is called the forward reaction, or the forward direction. The reaction of products to reactants is called the reverse reaction, or the reverse direction. Most of the time, the most dominant reaction, the reaction that happens to a larger degree, is written in the forward direction. These reactions are occurring simultaneously. They are both occurring all of the time, but that doesn't mean that they are happening to the same amount or have the same speed. The speed of a reaction is called the rate of the reaction, or the reaction rate. A rate is a change of something as a function of time. A speedometer in a car measures mph, miles per hour. It notes the change of distance, miles, as a factor of time, hours. We will see shortly that the rate of a chemical reaction can be expressed as the change in the concentration of a species in the reaction as the time changes. In the previous two lectures of this series, we looked at the role of energy in chemical reactions. Thermodynamics looked at the energy of a reaction. Energy answers the question of whether a reaction occurs as written in the chemical formula. Specifically, looking at the free energy, delta G of a reaction, answers the question of whether a reaction releases energy, negative delta G, and is spontaneous, or it consumes energy, positive delta G, and is non-spontaneous. The limitation with energy is that spontaneous does not speak to how fast a reaction occurs. It only implies that eventually it should. Eventually, diamonds will spontaneously be converted into graphite, as one might find in a pencil. But that reaction occurs on a geological timescale, so there is a need for a new branch of chemistry to look at the speed of a reaction by studying reaction rates. That, of course, is kinetics. Kinetics looks at how fast a reaction proceeds. So, what exactly is a reaction rate? Returning to the formation of water as a reversible reaction, a reaction rate is the change in concentration of a reactant or product over a period of time. Rate means change. As an equation, the reaction rate can be expressed as using either reactant or products. One form has the change, delta, of the concentration of a reactant divided by the change in time. At the start of the reaction, with a maximum amount of reactant, this change is a maximum. A maximum amount of reactants can be changed into products. As the reaction proceeds and there is less reactants, the change is less. The other form of the rate equation is from the perspective of products. It is the negative change of the concentration of the product over the change in time. The negative sign is a recognition that the concentration change of the reactants and products go in the opposite directions. The only way for the concentration of the products to increase is for the concentration of the reactants to decrease. The opposite is also true. The rate change for products at the start of the reaction is also at a maximum, since there is a maximum amount of reactant that can form a maximum amount of products. As the reaction proceeds and there is less reactant, there is less product form. More on rates in a bit, but as a heads up to the next lecture, equilibrium occurs when the rate of the forward reaction is equal to the rate of the reverse reaction. At that point, the change in concentration becomes zero. Equilibrium is a combination of kinetics and thermodynamics. So, kinetics, thermodynamics, and equilibrium are all different ways to look at the chemical reaction. But from the perspective of elements and compounds, a more intuitive way to look at reactions and kinetic rates is through collisions and energy. For a chemical reaction to occur, particles have to collide. That follows from our understanding of heat. Heat is motion. Atomic scale particles have heat, so atomic scale particles must have motion. And if there's motion, there are collisions. Importantly, collisions involve a transfer of energy. We see that when a cue ball collides with a rack of balls in a billiards game. With a chemical reaction, the transfer of energy can result in the making or breaking of bonds. The transfer of energy in a chemical reaction can be followed with a reaction coordinate. Thermodynamics has it that the energy transfer is just related to the energy difference between reactants and products. But energy is also needed to get the reaction to occur. That is the activation energy. For many reactions, old bonds are broken to make way for new bonds. The energy of breaking old bonds comes from collisions. The higher the activation barrier, the more energy that is needed to break the bond. But not all collisions have enough energy to break a bond. There are a number of factors that dictate the energy that a particle brings to a collision. One of them is the speed at which the particle moves. Faster moving particles can transfer more energy. However, with elements and compounds, speed is a complicated subject. Simply put, in a reaction, not all particles will have the same speed. Gases show this best. As we saw in the Gas Advanced Concepts lecture, the particles of a gas have a distribution of speeds. There are fast-moving particles, which have more energy, and slower-moving particles that have less energy. There's going to be a distribution of energies brought to the collisions. With this in mind, and collision as our guide, we can ask the question, what does it take to increase the rate of a reaction? We will limit the discussion to increasing the rate of the consumption of reactants. The short answer is to have more collisions with sufficient energy to overcome the activation energy barrier. That can be done in one of two specific ways. Increase the number of collisions, or increase the strength of the collisions. Let's spend time with both of these options, and we will refer to them as factors affecting reaction rates. The first option, increase the number of collisions. That can be done by increasing the concentration of reactants. If there are more particles, there are more collisions. If there are more collisions, then there are more collisions with enough energy to overcome the activation energy barrier. This is strictly based on statistics. An analogy would be that a high school with a larger population is more likely to send more students to the state track meet. Not that larger schools have faster students, is that with more students, there will be more fast students. Factor 1 is in place. Another way to increase the number of collisions is to raise the temperature. Higher temperatures mean higher average speeds. Again, from the Gas Advanced Concepts lecture, it was shown that raising the temperature shifts the distribution of speeds of the particles to faster speeds. Faster particles collide more often. They cover more ground. And as we just saw, from a statistical point of view, more collisions means more collisions with enough energy to overcome the activation energy. Faster overall particles also lend themselves to a second option of increasing reaction rates. Faster particles collide harder, and a harder collision will have a higher energy. Faster car crashes have more energy. So, now we have a second way to affect reaction rates. The third way is to add a catalyst. A catalyst is a compound or element not consumed in the reaction. It participates, but in the end, it is unchanged. The sole function of a catalyst is to lower the activation energy of the reaction. Bringing back the reaction coordinate, a catalyst can be shown to lower the energy barrier to the reaction. The hump is smaller. The new lower barrier means collisions need less energy to successfully overcome the barrier and complete the reaction. Without changing any other condition or any energy of collision, a larger percent of the collisions will meet the energy criteria. That is the third way. There are more ways, but they are specific to certain conditions of a reaction. For gases, increasing the pressure increases the number of collisions, since the particles are closer together. Pressure can be increased by decreasing the volume, increasing the temperature, or increasing the concentration of the particles. For solids, the shape or amount of surface area is a factor. Since most reactions take place on the surface of the solid, it makes sense that having more surface area leads to more successful interactions. Grinding up a solid is a sure way to increase its participation in the reaction. We saw that when looking at ways to increase the solubility of a solid in a liquid. All right, it's time to focus on rates themselves. Consider a reversible reaction. For demonstration purposes, we will say that the reactants forming products is the forward reaction and is favorable. Products reforming reactants is a reverse reaction and unfavorable. A way to demonstrate favorability is to alter the size of the reaction arrows. Instead of two equal size arrows, a large arrow is used for the favorable direction, and a small arrow is used for the unfavorable direction. That the unfavorable direction has an arrow at all indicates that to a small degree the reaction does go in that direction. Can an unfavorable reaction even occur? Yes, it can, if the energy of the collisions is sufficient to overcome the activation barrier. But compare that to the energy needed to get the favorable reaction going. Many more of the collisions of the reactants will have the energy to overcome this smaller barrier. That is why the forward reaction gets the big arrow. As to reaction rates, and starting with the rate of a reactant, using a reaction that starts with nothing but reactants, no products yet, the concentration of a reactant starts high and decreases to a constant value as time progresses. It gets used up. But at some point, in a reversible reaction, the concentration stops changing. What would that look like on a graph? Here's a set of axes, time on the x-axis, and the concentration of the species of interest is on the y-axis. As stated, the concentration of a reactant at the beginning of this reaction is at a maximum. But as the reaction proceeds, the concentration decreases as the reactant is consumed in the reaction. It reaches a point, however, where the amount of reactant consumed in the forward reaction is matched by the amount of reactant produced in the reverse direction. Returning to the start of the reaction, the concentration of a product starts low, like 0, and increases to a constant value. On the graph, that has a concentration near 0 and increasing as the reaction continues. Product is formed. As with the reactant, there comes a time when the amount of product formed in the forward reaction is matched by the amount of product consumed in the reverse direction. There is a point where the concentration stops changing. Not that the forward or reverse reactions stop, but they become matched. How does a favorable and unfavorable reaction become matched? Well, it has to do with concentrations at this point in the reaction. Comparing the concentration of reactants and products shows that there is much more product than reactant. There's very little reactant to make more product, but there's a lot of product to make reactant. Even though few of the collisions between the products have sufficient energy to overcome the activation energy barrier and make reactant, enough of them do to match the loss of reactant in the forward direction. At this point in the reaction, the rates of the forward and reverse reactions are equal. Concentration and energy drives the matching. To that point, from an energy perspective, the bigger the energy difference between the reactants and products, the smaller the reactant concentration will need to be to get this matching to occur. With the role of concentration in hand, we can directly compare rates. Early in the lecture, rates was mathematically defined for reactants and products. The rate of the forward reaction is given as the concentration of a reactant over a change in time, delta time. That will be equal to the negative of the rate for the reverse reaction, the change in the concentration of a product over delta time. In a manner similar to how we looked at the change in concentration as a function in time, we can look at the rates of the forward and reverse reaction as a function of time. The y-axis is the rate reaction with a rate of 0 at the center. The rate of the forward reaction starts high and decreases to a constant value. Graphically, the rate of change of the reactants is high in the beginning. That is where the concentration of reactants is a maximum. And as time goes by, the rate decreases. Consulting the concentration graph shows the concentration to rapidly decrease over this same period of time. With less reactant, the rate of change of concentration should go down until the concentration stops changing. At this point in the curve, the rate of the reactant is 0 because the change in concentration is 0. Rate is change. Rate of the product starts low. There's initially no product and increases as the reaction proceeds. That tracks with what we see on the change in concentration of product as a function of time. At some point, the concentration of product stops changing and the rate of the product stops changing. No change in rate is 0. Where there is no change in concentration, there is no change in rate. This puts us at the topic of the next lecture, equilibrium, and we will introduce it here as a way to tie up kinetics. Keeping these graphs for reference, a reaction is at equilibrium when the forward and reverse rates are equal. They are equal when the concentrations have stopped changing. That does not mean the concentrations are equal. It does mean that the concentrations are not changing. The equal in equilibrium is for the rates. That's enough of a start on this busy topic. As a recap of the lecture, under the right circumstances, products can react to reform reactants. This is called a reversible reaction. We used a generic reaction equation to show many of the concepts of the lecture. Here, reversible reaction is shown with the double arrows. Kinetics looks at the rates of reactions. The rate is the change in concentration of a species in the reaction over a change in time. There's a rate for the reaction moving forward as written, and one for the reverse of the reaction as written. For a chemical reaction to occur, particles have to collide. Energy has to be transferred. There are a number of ways to increase the rate of a reaction. One is to increase the number of collisions. That can be done by either increasing the concentration of the particles or the speed of the particles. Increasing the temperature will speed the particles up. Another way is to increase the strength of the collisions by increasing the speed of the particles. Again, add heat. Looking specifically at rates, at the start of a reaction with only reactants, the rate of the forward reaction starts high at the beginning of the reaction and decreases to a constant value. Reactants are used up to a point. The rate of the reverse reaction starts low at the beginning and increases to a constant value. More products are being made to a point. At equilibrium, the forward and reverse reaction rates are equal. And that concludes the lecture. Remember, kinetics is about the speed of the reaction.